Good morning, everybody.
Good morning, sir.
So as a reminder, we're going to have our second exam on Wednesday. We'll post it online, and you'll have the scheduled time to return it. Now, also, I have some good news, which is probably this week is the week we're going to also post the project for the class. So in case you're bored or feeling like the semester is not as busy as you expected, you'll have something to add to your agenda. Okay. So what we're going to do today is we're going to talk about frequency transformation, and then we're going to start the second type of filters, which are the FIR filters. So our topic is frequency transformation. So in the previous class, we learned how to design a low-pass filter, Butterworth, Chebyshev, using any of the method, impulse invariance, the Mass-Z transform, or using bilinear transformation. What we're going to learn, or what we're going to introduce now, is how to take that filter and convert it into any other type of filter, a bandstop, a high-pass, a bandpass filter, from the low-pass filter design that we studied. So the question we're answering is how to design a digital IIR filter or filters that are not low-pass filters. And to do that, there are two methods of doing this. So one of them, we're going to call it continuous time domain. And the other one, we're going to call it transformation in the digital domain. So in the continuous time domain transformation, we're going to design a low-pass filter, then we're going to apply frequency transformation, and then we're going to convert the filter after we transformed it to a digital filter. So frequency transformation. So here we can have a bandpass filter, a high-pass filter, but it's still a continuous filter. Then we're going to do the conversion. And then this will give us the digital filter that we want. So we're going to design the low-pass filter. We're going to do frequency transformation. We're going to get any of the filters we're trying to design. Then we're going to convert the transformed filter to the digital domain. Now in the second method, we're going to design a digital low-pass filter. And then we're going to use a table that converts to different filter types. So we apply transformation. Based on a set of formulas. Okay. Now the method that we're going to be covering, and I thought I had the slide for that. Okay, looks like I don't. don't. Okay, the method that we're going to be covering is this method, which is the design a low-pass filter, then do the frequency transformation, then do the conversion to a digital filter. This method is more intuitive, and the math is easier. And we already studied the math to do the filter design. Again, in the second method, you design a filter. There is a table that tells you if you're going to transform to this bandpass filter. This is how you transform it. You have to replace C with a set of formulas. And the formulas are in the book in a table. Okay, so with that, we can start our frequency transformation. And we're going to see how we can take any filter and convert it to any other type of filter. So let's start first. If we have a normalized low-pass filter, how do we convert it to a low-pass filter? This is one thing you already know.
Plug in for S.
Yes, we replace S with S over omega C. So if I have a normalized filter that looks something like this, and I want to convert it to a low-pass filter that has a certain cutoff frequency, all what I have to do is to replace S with S over omega C. Omega C. Makes sense? When omega is equal to omega C, it's going to be omega C over omega C, which is a 1. So this point is going to correspond to a 1. And when S is less than omega C, it's going to correspond to this region here. When S is greater than omega C, it's going to correspond to the region outside of the omega C. Okay. The second filter. What happens if we have a normalized low-pass filter and we're going to convert it to a high-pass filter? So again, we have a filter that is from -1 to 1. And I want to convert it such that it looks something like this. What do I have to replace S by?
Omega over S?
Oh, excellent. Omega C over S. If you replace S by omega C over S, then the low-pass filter is going to be converted to a high-pass filter. Again, when omega is less than S, which is when omega is less than omega C, which is this region here, then this is going to become greater than 1, which is going to correspond to this region here. Does it make sense? When omega is less than omega C, which is this region here, when I plug in for S a value of omega that is less than omega C, then omega C over S is going to be greater than 1, which is going to correspond to this region. And the same thing, when omega is greater than omega C, then this is going to be less than 1, which is going to correspond to this region here. Together? Okay. What happens if we have a normalized low-pass filter and we're going to generate a bandpass filter? Now this is less intuitive, and therefore will give you the formula. I want to take that filter and I want to convert it to a filter that might look something like this. I have W lower, W upper, and this is the bandwidth. And in order to convert a normalized low-pass filter to a bandpass filter, we need to replace S by S squared plus omega 0 squared divided by B multiplied by S. Where omega 0 is equal to the square root of omega upper multiplied by omega lower, and B is equal to omega upper minus omega lower.
So just plan omega upper and lower, not square.
No, because we're multiplying them.
Got it.
It's going to be squared, and square root will go back to omega. Okay. So to convert a low-pass filter to a bandpass filter, we're going to use this formula. We're going to replace S with S squared plus omega squared, omega 0 squared, divided by B multiplied by S, where B is the bandwidth, omega upper minus omega lower, and omega 0 is equal to the square root of omega upper multiplied by omega lower. Why is that the case? How does that work? I mean, let's try to plug in some values for S. If S is equal to J omega L, so let's see where this point will be transformed using this formula. So if you do that, we have J omega sub L squared plus omega sub L multiplied by omega upper divided by B, which is omega upper minus omega lower multiplied by S, which is J omega L.
Sorry, what is in the replace S by, what is that? It's WB squared? My eyes are bad.
S squared plus omega 0 squared divided by B multiplied by S.
Okay, thank you.
And I'm sorry, for the numerator of that fraction on the bottom, is that WL times WU?
For the numerator here?
The bottom one, that one. So is that WL times WU?
Yeah.
Okay.
Omega 0 squared
root.
is square root of this squared. Okay. So therefore, we can write this as negative omega L plus omega L multiplied by omega upper
It would be omega L squared.
divided by J multiplied by omega lower
I guess he cancels one out.
multiplied by omega upper minus omega lower.
So where'd the square go?
Which square?
So you squared the J. Forgot to square the
Oh, there is a squaring of the J, negative omega L squared. Okay, so what is this equal to? We can take omega L outside here. So you're going to have omega L multiplied by omega upper minus omega lower divided by J multiplied by omega L multiplied by omega upper minus omega lower. And these will cancel each other.
The second.
And we're gonna,
At the top, the second one.
this should be upper minus lower. And this is gonna give us a negative J multiplied by a 1. which is omega equal to -1. Together? So this means this omega lower is going to correspond to whatever value this omega equal to -1 corresponds to. And we can try the same thing with omega upper. Omega upper is going to correspond whatever value here. If we do the same substitution, it's going to correspond to this one. Does that make sense? So anything in between is going to correspond to the pass band. Anything outside is going to correspond to the stop band. Together? Make sense, everybody?
Yeah.
Okay. Now what happens, one thing we have to mention here is that when we do a filter that is a bandpass filter, what's going to happen to the filter order is going to double. Why is the filter order going to double? Because of how we're replacing S. We're replacing S by S squared.
Yeah.
So if the filter was fifth order, we're going to double that. Make sense?
Yeah.
So the bandpass and the bandstop filter will double the filter order. So let's just write a note here that the filter order doubles. Okay. Okay, let's see if we have a band, if we want to design a band stop filter. So if the fourth filter type we're going to see is a normalized low pass filter to a band stop filter. So this is our upper, and this is our W lower. This is the bandwidth. And similar to the band pass filter, if we replace S by B multiplied by S divided by S squared plus omega 0 squared, then we're going to convert the normalized low pass filter into a band stop filter, where omega 0 and B have the same definition. This is the square root of omega lower multiplied by omega upper, and B equals to omega upper multiplied by omega lower. And similar to the bandpass filter, the filter order here is also going to double.
So omega upper minus omega lower, right?
B is omega upper minus omega lower.
Yes. Right.
Okay. Together? So with this transformation, we can take any normalized low-pass filter, convert it to any of these filters, and then we can take this filter and convert it to a digital filter. So let's look at the design steps, and then we'll do some examples on the filter, on designing the filter. Now the project that I'm gonna assign is gonna be mainly building all these filters and filtering some signals. I mean, you see the math involved is rather involved, so it's easier to do it with as a project. Now we're gonna design all these filters using bilinear transformation, because the bilinear transformation what is the advantage of the bilinear transformations versus, for instance, the impulse invariance?
Less aliasing.
There's no aliasing, and therefore we can design a high-pass filter and a bandstop filter. Otherwise, we won't. Okay, so we're going to pre-warp all critical frequencies. So if we have our filter, okay, so we have a high-pass filter. So this is going to be our cutoff frequency, omega cutoff. This is going to be our omega stop. If we have a bandpass filter, this is going to be our omega stop lower. This is omega cutoff lower. This is going to be our omega cutoff higher or upper. And this is going to be our omega omega stop upper. And you see the logic? Close to where there is high attenuation, the stop. So this is stop, this is stop. This is cut off from the pass band. Close to the pass band is the cutoff. Cutoff, cutoff, stop, stop. This is lower, this is higher. Or lower, this is upper. Okay, similar thing here. Now here we have omega cutoff lower, omega stop lower. We have omega stop upper, and omega cutoff upper. Okay, so after we pre-warp all the frequencies, we're gonna map the pre-warped frequencies to equivalent low-pass filter. And if we are designing a high-pass filter, then omega nu is going to equal to omega cutoff hat divided by omega. If we are doing a bandpass filter, then omega nu is going to equal to omega 0 squared minus omega squared divided by b multiplied by omega, where b is going to equal to omega cutoff upper hat minus omega cutoff lower hat, and omega 0 is going to equal the square root of omega cutoff upper hat multiplied by omega cutoff multiplied by omega cutoff hat. Okay. And I made a type cutoff upper and stop upper. So I'm going to take these two frequencies, two frequencies.
The bandpass will be C upper and C lower.
For the band stop,
The bandpass for a B.
Oh, sorry. What was the omega 0 is the cutoff. So I take that back. I should not have intervened. Upper, cutoff lower. Sorry. Cutoff upper, cutoff lower. Okay. We are doing a band stop filter. W nu is going to equal to B multiplied by W divided by omega squared minus W squared. And the same definition for the B and omega 0. Okay. So then we're going to design normalized low-pass filter that is continuous. And you can tell by looking at these, we have two sets of frequencies, unlike the high pass filter. Here we have one set of frequencies. Here we have two sets of frequencies. 1, 2, 1, 2. So therefore, when we design a bandpass filter, we're going to get two sets of low pass specifications. Does that make sense? So what we're saying, when we design the high-pass filter, we have one set of frequencies. Here we have two sets of frequencies. And therefore, when we design the filter, we're going to use the tighter of the two sets. And we'll see what that means when we do an example. Okay. So after that, the next step, we perform the frequency transformation. And if it is a high-pass filter, we're going to replace S with omega C hat divided by S. If it is a bandpass filter, we're going to replace S with S squared plus omega C lower hat multiplied by omega C upper hat divided by omega C upper hat minus omega C lower hat multiplied by S. And if it is a band stop filter, we're going to replace S with omega C upper hat minus omega C lower hat multiplied by S divided by S squared plus omega C lower hat multiplied by omega C upper hat. The next step is we do bilinear transformation. And finally, we set the filter gain. What is the default filter gain if it is not specified? 1. If it is a low-pass filter, then at omega equal to 0, the gain should be 1. If it is a high-pass filter, then at infinity it's a 1. So unless it is stated otherwise, but the default is 1. Okay, so with all that, let's do an example. So in this example, we're going to design a high-pass filter that is Butterworth and using bilinear transformation. And the specifications for the filter are as follows. So our 3D point, the omega cutoff, is equal to 2 pi multiplied by 2000 and omega stop is 2 pi multiplied by 1000 and the attenuation is 20 dB. And the sampling frequency is equal to 10 kilohertz. Again, omega cutoff is 2 pi multiplied by 2000. Omega stop is equal to 2 pi multiplied by 1000. And alpha is equal to 20 dB. Okay. So the first step is to pre-warp all the frequencies. So we're going to calculate omega c hat. It's going to equal 2 over t multiplied by tangent of omega cutoff multiplied by t divided by 2. And that is going to give us a 14,530. We're going to pre-warp the stop frequency, omega stop, 2 over t, tangent of omega stop multiplied by t divided by 2 is going to equal to 6,498. Together? What do we notice? What is the frequency, the cutoff frequency here? It's 4 multiplied by 3.14, which is around 12. So in order to correct for the warping, we convert it to a 14. The stop frequency is 2 multiplied by pi, which is around 6. We change it to 6.4. Make sense? Is that consistent with what we know? Yes, because the higher the frequency, the more the warping is. So when we calculate these, and always when you calculate them, I mean check them with the original values, because just to make sure you calculate them correctly, they should be close to the original values. And that will give you a sanity check. Okay, the second step, we're going to map to low frequency normalized filter to low pass normalized specs. And therefore, omega nu is going to equal to 14530 divided by W. Therefore, we're going to calculate omega c hat is going to equal to 14,530 divided by 14530, which is going to equal to just a 1. And then we're going to calculate omega stop hat, which is going to equal to 14530 divided by 6,498, which is going to equal to 2.23. So we took the high-pass filter and we converted to a normalized low-pass filter. So this low-pass filter is the filter that we're going to design now. has the specifications that look something like this. The cutoff frequency is 1, and the stop frequency is 2.23, and this is a negative 20 dB, and this is my 3 dB. What do I need to do next? I need to find the filter order. This and the alpha will determine the filter order. So I'm going to take 10 multiplied by log 1 plus omega stop hat divided by omega cutoff hat to the power of 2n. I want it to be greater than or equal to a 20, and that will give me n that is equal to a 3, that will result in a 21 dB. And maybe I'm going to just add an n here, n here, n here, n here. Good? So like the notation is consistent because we used omega stop here. So I'm going to call it omega cutoff new, omega stop new. So we're not using the same notation twice.
Yeah, that makes sense.
Okay. Okay, so we can go to the table and we can get our, and this is step number 3. We can get our normalized filter from table. We have HC of S that is equal to 1 over SC cubed plus 2S.
Hard crash.
How far back did we go? Oh, we did not lose anything.
Made.
Okay, since this word caused the crash, I'm not gonna write it again. I'm gonna write it in another place. From the tables, SC of S is gonna equal to 1 over SC cubed plus 2S squared plus 2S plus 1. Okay.
Unnormalize.
Ready? Okay, the next step is to unnormalize. So therefore, we're going to have to take S and replace it with 14,530 divided by S. So therefore, H of S is going to equal to 1 over 14,530 divided by S cubed plus 2 multiplied by 14,530 divided by S squared plus 2 multiplied by 14,530 divided by S plus 1. What is this going to give us? SC cubed divided by SC cubed plus 29061 S squared plus 422,291, 203S plus 3 times 10 to the power 12. Now it is true, when you're doing this calculation, you're going to get some huge numbers here. But eventually, they're going to cancel out and go back to being the normal numbers. So don't be alarmed if you see a very large number while you're doing the calculations. Okay, so we have H of S. This is of a high-pass filter that has a cutoff frequency of 1453. Now we need to do apply bilinear transformation. So the next step is to apply bilinear transformation. So we're going to need a queue that is a 4x4, which is going to have entries that are 1, 1, 1, 3, 3, 1, 1, negative 1, negative 1, negative 1, negative 1, 1, negative 3, 3, and negative 1. And since h of s is already unnormalized, we have c that is equal to 2 over t, which is going to equal to 20,000. And we can generate the numerator. We have b hat that is equal to 0, 0, 0, 1 multiplied by 20,000 cube. C to the 0, c to the 1, c squared, c cube. 1 is coming from the numerator. Okay. So then we can calculate b for the let's do the denominator too. B hat denominator. So if you like, this is n, this is denominator, is going to equal to 3 times 10 to the 12, 4, 2, 2, 2, 9, 1, 2, 0, 3, 2, 9, oh, this is multiplied by c, so this is multiplied by 20,000. Then we have 29061 multiplied by 20,000 squared, and then we have 1 multiplied by 20,000 cubed. Okay. So then we're going to multiply q by the transpose of these to get the numerator, q by the transpose of this to get the denominator, and that will give us the numerator .8, negative 2.4, 2.4, negative 0.8, multiplies by 10 to the 13, and d for the denominator is going to equal 3.11 minus 1.79, 1.3 minus 0.175 multiplied by 10 to the power 13. So the 10 to the 13 will cancel out, and we can write our h of z, which is going to equal to k multiplied by z cubed minus 3 z squared plus 3z minus 1 divided by z cubed minus 0.577 z squared plus 0.42 multiplied by z minus 0.0563. We divide it by the first entry to normalize it. So if we divide by 0.8, this is going to become a 3, and negative 1. And the same thing with the numerator. Okay. What is the last step? To set the value of k. Okay. So to set the value of k, you set to the gain equal to 1 at,
7.
sorry?
This be step 7.
It is step 7. Thank you. Set the value of gain equal to 1 at omega equal to a pi, and omega equal to a pi corresponds to z equal to -1. So therefore, we want h of -1 to equal to a 1, which gives me k that is equal to 0.2569.
But where did you get to z -1?
Why?
Here.
Because omega, because I need to set the gain at a very high frequency, because it's a high pass filter. A high frequency, what is the highest frequency in discrete time? Pi. What is pi corresponds to in z? 1. Remember? This corresponds to omega equal to a 0. This corresponds to omega equal to a pi. And if this is the z, this z equal to a 1, this is z equal to -1. Make sense? Z equal to -1 corresponds to omega equal to a pi, which is the highest frequency.
Can I see briefly the last page, like the bottom of the last page real quick? All right, thank you.
This one, just divided by the first entry.
And the second one says 3.8.
Yeah, whatever the first entry in.
3.1.
Okay. Yeah, I forgot I was not even gonna do these calculations here. I was gonna let MATLAB do it. Okay, so I'm gonna paste this in. These are the same numbers that we have, but just calculated with MATLAB. And this is our filter. And this is our numerator and denominator. And we can see here, when we are at 0.2, oops. When we are at 0.4, that will correspond to -3 dB. And when we are at 0.2, that corresponds to the attenuation requirement, which is at 20 dB, which we are exceeding it. Okay. Now this was an easy example. Let's do something more interesting. Okay, so these are the numerator, denominator calculations. Okay, so let's do another example. And what we're going to design Anybody feeling exhausted with designing filters?
Isn't this what this class is about?
Okay, so if you are getting exhausted, this is the last filter, IIR, that we're going to design.
Then we move to FR.
Yeah. But that will be a different beast, so it will be exciting at the beginning. Okay, so we're going to design a band stop filter. And the filter has the following specifications. So we want our filter we have omega cutoff lower, omega stop lower, omega stop upper, and omega cutoff upper. And for this filter, the sampling frequency is 5 kilohertz, and we have a ripple that is equal 1 dB. We have alpha that is equal to 10 dB, and omega cutoff lower equal to 2 pi multiplied by 500. Omega stop lower equal to 2 pi multiplied by 750. And omega stop upper equal to 2 pi multiplied by 1250. Omega cutoff upper equal to 2 pi multiplied by 1500. And we're going to design, apparently this is a Chebyshev filter, type 1 filter, and we're going to use bilinear transformation. Okay. So again, the first step, we're going to pre-warp frequencies. Omega hat is going to equal to 2 over t, tangent of omega multiplied by t divided by 2. So this is going to give me omega cutoff lower hat equal to 3245, omega stop lower hat equal to 595, omega stop upper hat is going to equal to 10,000, and omega cutoff upper hat is going to equal to 13,764. And I'm going to put one of the calculations here. So this is 2 multiplied by 5,000 multiplied by tangent of 2 pi multiplied by 500 divided by 2 multiplied by 5,000. Is 1 over t. Okay. Okay, the next step, we're going to map these frequencies to normalized low-pass filter specification. So we're going to use B that is equal to omega cutoff upper hat minus omega cutoff lower hat, which is going to give me 10,519. And we're going to calculate omega 0. So this is this and this. We're going to calculate omega 0, which is square root of omega cutoff upper hat multiplied by omega cutoff lower hat, which is going to equal to 6683. And therefore, we can transform the frequencies using omega nu is going to equal to BW divided by omega 0 squared minus W squared, which is going to equal 10519 W divided by 44,662,489 minus W squared. Okay. So then we're gonna use the transformation to take all these frequencies and transform them. So this is gonna give us omega cutoff lower hat. We're gonna call it L equal to 1. Omega stop lower hat. We called it N before, so let's call it N. N equal to 2.868. Omega cutoff upper hat nu equal to -1. Omega stop upper hat nu equal to -1.9. So you see what happens here? Now we have two sets of frequencies. We have this and we have this. Which one of these is tighter? The one on the right. Isn't it? This is 1.8, this is 0.9. Everybody knows what I'm talking about? Okay. So here we have a 1.8 transition. Here we have 0.9 transition. So this is a tighter limit to meet. So therefore we use it to design our specs, to design our filter. Okay. So therefore, we're going to design our low-pass filter. So the third step, design low-pass Chebyshev filter. We have epsilon equal to 0.51. That is coming from R equal to 1 dB. So therefore, we want 10 multiplied by log 1 plus epsilon squared Chebyshev polynomial squared of 1.9 divided by 1 to the power of, oh, there's no power, greater than or equal to alpha, which is equal to a 10. So we're going to find the order of the polynomial that is going to meet that, and that is going to be n equal to a 2. Where is the 1.9 and 1 coming from? From the tighter limit that we chose to design the filter. Okay, so therefore, we're going to go to the tables. We're going to get h of s, that is equal to s squared plus 1.0977s plus 1.103 Okay, so then we're going to do frequency transformation. We're going to replace S with omega C upper hat minus omega C lower hat multiplied by S divided by S squared plus omega C lower hat omega C upper hat, which is going to equal to 10,519 multiplied by S divided by S squared plus 44662 489. Okay. So we're going to calculate H of S. We're going to have S squared plus 44662 489 squared divided by 10519 multiplied by S squared and this is going to give me S to the 4 plus 89 324 978 S squared plus 1.9947 times 10 to the 15 divided by 1.103 S to the 4 plus 11,546 S cubed plus 209 174 811 S to the squared plus 5.15 times 10 to the 11 S plus 2.05 times 10 to the 15. It's unfortunate, but these numbers are huge, even though at the end they're going to cancel out. But I'm going to run it with MATLAB, and MATLAB will do all these calculations. So that's why I skipped some of the simplifications here. So when we run MATLAB, we'll see all these numbers. Okay. The next step, we're going to do bilinear transformation. And Q is going to be a 5 by 5, which is going to be 1 1 1 1 1 4 6 4 1 2 0 negative 2 negative 1 0 negative 2 0 1 1 negative 2 0 2 negative 1 negative 4 6 negative 4 1. And C is going to equal 2 over T, which is going to equal to 10,000. Okay. Okay. So then for the denominator, we're going to calculate the denominator. We're going to calculate the numerator. We're going to calculate B hat which is going to equal 2.055 times 10 to the 15, 1.103, 1.0103 times 10,000 to the 4. Then we're going to calculate D, that is equal to Q multiplied by B hat, which is going to give me 5.07. And again, we'll see all these numbers with MATLAB. That's why I'm not writing them. And we're going to do the same thing with the numerator. B hat is going to equal to 1.9947 times 10 to the 15, all the way to 1 times 10 to the 10,000 to the power of 4. Now all these are transposed when you multiply them. Everybody knows that. You cannot multiply 5 by 5 with 1 by 5. So you can write transpose here if you like. This is going to be 2.09 times 10 to the power 16. And this will give me h of z, that is equal to z to the 4 minus 1.53 z cubed plus 2.58 z squared minus 1.5z plus 1 divided by z to the 4 minus 0.96 z cubed plus 0.72 z squared minus 0.45 z plus 0.34. Now before I forget, it looks like, so we're going to run the MATLAB to get all these numbers that we, but I'm going to go back to the high pass filter. And I just want to write the MATLAB equation, which we have in here, but I want to tell you where it's coming from. BA equal to butter 3, and then 2 multiplied by 2,000.
You got it right there, right?
I guess I have it right there, yes. Over 10,000 and high. Okay. Now for this filter, I'm going to write the MATLAB as you have it in here. BA is going to be chippy 1. 2 is the filter order. 1 is the R. And 2 times 500 divided by 5,000. This is the cutoff. This is 2 multiplied by 1,500 divided by 5,000. And this is S top.
Two times 500 or 2 pi 500?
No, 2 times. Multiply.
Okay.
Yeah, MATLAB tells you give me whatever multiplies the pi. Okay, so let's run the MATLAB. Okay, so first, what is the difference between these two filters? with the same filter. One in dB and one in this magnitude and different scale, different range of frequencies. So if I take this, plot it in dB, it's going to look like this. So both of them the same. Okay.
So why do you plot the phase here?
Why not?
What does it tell you?
Good question, because that is going to be, that's why I asked you. First of all, this is plotted automatically with the Z command. Okay. But it's good that you asked that we should always look at the phase. What does the phase tell me? And this is probably a good intro to our FIR filter.
If it's differential?
If the phase is linear, then the filter does not cause any distortion to the signal that is coming in. Does that make sense? Yeah. Anybody remembers this from? Did you see this before? Okay, maybe we'll do an example next class. But if the phase is linear, if I apply two sinusoidal signals with different frequencies, they're going to be delayed by the same amount of time. So they go and sinusoidal signals, they go out attenuated at different magnitude, but they're the same delay. If that is the case, the phase has to be linear. If the phase is not linear, I put in two sinusoidal signals with different frequencies. One is going to go out fast, the other is going to go slow, it's going to distort the signal. Does that make sense? So linear phase is always something that is desired because it means there is no distortion to the signal. Okay. I know we're getting to the end of this, but we'll run this, and please also, when you go home, run it. So I'm going to just copy it and paste it. And I intentionally wrote these numbers here so you can see them. Does that make sense? Or I could have written a script that will do all this automatically, but I wanted to see the numbers so you can cross-reference them with the solution that we had and fill, if you like, the missing numbers. Okay, so, but nevertheless, at the end of all this, we get the numerator of h of z and the denominator of h of z, which is what we had there. Sounds good?
Yeah.
Everybody?
Can you show the previous page for a second?
The MATLAB?
No, the previous page of the notes. Got it.
Okay, thank you, everybody. We'll see you on Wednesday.